Hey there, in this video we're giving some final thoughts as we reach the end of the first semester of Starter C++ programming. And if you think all the way back to the beginning of our lecture sequence, among the very first things we said is that computer science is arguably the most challenging thing that humans have ever done, the most complicated thing. There's so many details, there's so many things that we covered in this first semester. And, I would tell my students frequently at the end of the semester, do I expect them to remember every single detail we ever talked about? Well, probably not, of course. If you're doing work as a computer programmer, you frequently need some resource materials. Maybe they're online that you look up to refresh yourself on all the details. But there are some things that I honestly do hope will stick with you forever, frankly. And so this video here gives some conclusions about what I think the most important things to keep in mind are that I do want you to have in your head, hopefully forever. Okay, so first of all, let's think about the distinction between procedural and object-oriented programming that we just started to get a little taste for right at the end of this first semester. This course, Programming 1, has mostly been about what we'd call procedural programming basics. Later courses will probably be more about what's called object-oriented programming. So procedural programming this first semester is where your data and your functions or procedures, however you want to call them, are defined in separate steps. Your data, your variables, are a separate thing from your functions and procedures. Remember, procedures is really a synonym for functions. And so we've been dealing with these two things separately, and you pass data into a function and you declare the variables separately. But the next step in programming paradigms would be what's called object-oriented programming, where your data and your functions are combined into these single entities called objects. And we started to see that in practice when we were talking about file handling. So among the reasons I'm glad we talked about that is just to dip our toe into a little bit of object-oriented programming. We had these file stream objects that contained functions, things you could do like open or close or check the fail bit or things like that. And it also internally contained information, data about where this file is on the hard drive and how far I've read into it so far, things like that. So that was fairly convenient to have those things packaged, and then you can think about one single file as a file stream object, and it just conceptually made a lot of sense to treat it like that. So that's going to be the main emphasis that we'll want to get to in second semester programming, Programming 2. But that's kind of a major switching point between the two semesters there, and that would be the goal for what happens in the future. Probably most professional programmers nowadays are working in an object-oriented programming paradigm. So we do need 2 semesters to cover all the basics of that. And this first semester was all the procedural stuff. And then you package it all together, all that stuff together, and then you've got object-oriented programming. And to be perfectly clear about it, and this is a little bit of an inside joke that I point out in second semester all the time, that's what the name C++ means. Of course, we know that plus means to increment something, means to add one thing. Well, the name C++ is actually kind of an inside joke that they took the C language, which is all just procedural programming, and they added one thing to it, namely object-oriented programming. And that's where the name C++ comes from. We took C, added one thing, objects. And that's going to be second semester. Now, one of the things that's interesting in this first semester of programming is that all semester long, we've basically been looking at things that are pretty much the same in a number of related languages, C and C++ and Java, and probably some other stuff like Objective-C and C# and so forth. So let's review that. This provides a pretty good review of everything we've talked about all semester. In this course, we've mostly focused on basic structures shared by all these languages, C and C++ and Java. From day to day, I was always talking about what happens in those other languages. Your basic data types, int, float, char, bool, double, exactly the same. Literally no difference at all. Those fundamental data types baked into the languages, exactly the same. There's no differences. The way that you make decisions, like back in chapter 4, the if-else statement, 100% the same. The switch statement, totally the same. Also, the ternary operator, the question mark colon operator, 100% exactly identical in all of these languages. No difference whatsoever. Your loops, Like the do loop, the do while loop, the for loop, 100% totally the same. No difference. The idea of functions, right? Function calls are the same in C. In Java, you call them methods, but it's the same idea after all. The idea of using arrays is the same in all of these languages. That's the basic way that you handle a lot of data using arrays. And then, the languages might do something else for more sophisticated stuff, but they all have arrays as your basic building block for lots of data. File handling concepts, all of these languages can handle file input and output. It might look a little bit different, but the idea is the same. You have to make a variable to handle the file object. You have to open it, you have to read or write, you have to close at the end. That's the same. Command line arguments coming into the main function as an array of strings, that's the same in all these languages. So we've been talking about C++, but the little secret is you've really gotten at least 3 languages all at the same time, kind of for free, which is kind of nice, I think. So that's among the reasons why I like starting with C++, is that all this information from first semester programming is pretty much the same, and you could just step over and declare yourself, now I'm a C programmer, now I'm a Java programmer, with these basic elements, because they're totally identical in these languages. Okay, but there are some differences. So let's just kind of highlight that. On the day, sometime in the future, where you do need to move to another language, let's just think about these differences that you're going to see. Now, the main thing that I think about for C is that C has no objects. It has no built-in string type, because the string type that we use in C++ is object-oriented, and that doesn't exist in C. So among other things, C has no built-in string type, and for strings, your only option is you've got to use C strings, which again are character arrays with a null terminator. So whereas in C++, we have these options. I could use C strings, I could use C++ string objects, but in C, you've got to use character arrays. You don't have any other option. And that's kind of why I'm glad that we talked about that a couple times. So if you do need to move to the older C language, you're ready for that. Now, one of the things about C++ that's totally unique are these sin and count objects, the IO stream objects sin and count. And it's kind of funny because sometimes that feels like among the most basic things we ever do, but that actually itself is among the weirder things about C++. It's almost the only thing that we saw this semester that doesn't look like these other languages. In other languages, it's more conventional to be calling functions, like print for output or maybe scan for input is more common. Specifically in the C language, if you're doing output and input in the C language, you're probably going to use printf and scanf for printing formatted text and scanning formatted text. And you'd have to learn how those functions work exactly. But that's really more common in other languages. The sin and the count with the left arrow, right arrow, that's unique to C++. And you don't see that object with left arrow, right arrow in other languages. Now, the interesting thing about Java, talking about arrays, right? We said the biggest single danger in all of programming, particularly C and C++, is buffer overflows. Having an array, making a little bit of a mistake, maybe just an off by 1 error, overwriting the array, trashing some other memory, and then crashing the program or other programs or your whole system. So, yeah, that might be arguably like an embarrassing thing about C or C++, but that's just how computers work, so that's how these languages work. Now, Java does something else, and maybe you already know that if you know a little bit about Java. Java does do automatic array bounds checking, so that issue is impossible in Java. Java will not let you overwrite the end of an array. It stores the size of an array automatically, whereas in C++, we were responsible as programmers for tracking that ourselves and might possibly accidentally screw it up. And therefore, Java prevents overwriting arrays. There's a system in Java that basically acts like a traffic cop, checks where you're writing an array, and if you try to go past the end of the array, it just prevents the whole thing. So there's some advantages, right? A Java program is hypothetically somewhat more secure. The buffer overflow issue just simply doesn't exist. But on the other hand, Java programs are always going to be a little bit slower because of this extra system in there playing traffic cop to check on that all the time. And hypothetically, if you never made a mistake with your arrays, that extra system time on the CPU is just a big waste. Now, this is the constant eternal debate between C++ programmers and Java programmers, is which of those strategies is better. And the Java program would say, I want to be safe and never worry about any disastrous, catastrophic mistakes, which like I myself have in fact done myself in the past. And the C++ program would say, I want maximum speed. I'm using this language to control really important, valuable things like rockets being shot into space, or AI-driven cars, or mental neural links to people's brains. It's so important. I want maximum efficiency, maximum speed. I'm going to handle that particular issue myself. And those are the pros and cons of those two sides. Okay, so that right there is kind of a big difference with Java, and arguably that's a good idea. Okay, so we've started with C++. I think it's a good starting point because it's so closely related to these other languages that you can very easily just step into one of the other languages. As a side point, Deb C++ will actually compile C programs. So if you take a file and just rename it from CPP to .c, and you switch out all the sins and couts for printfs and scanfs, you're a C programmer at that point. And you can actually use Dev C++ to do that. So there are many programming languages in the world. Depending if you're going to become a software engineer or a programmer, you might have to work on a number of different languages, and it's going to depend on what kind of job you're doing. So different particular jobs are better suited for different languages, and let's just think about what those cases are so you have an idea about what languages you might use for those jobs. Okay, so the C language, right, originally came up in the 1970s, the early 1970s, the older C language. Great for low-level stuff, nitty-gritty stuff like writing an operating system. Windows was originally written in C. Linux, which actually is the superstructure for the Apple iOS and Android devices, all that kind of stuff, written in C. The C language is for writing operating systems or embedded systems like important hardware. We create compilers, like the compiler we use was written in C. Very fast library modules, modular parts of larger programs that you need to be very, very super fast. You're probably going to write that stuff in the C language. Okay, now C++, which of course is what this course has been about, came up in the 1980s, more or less, just the start of it. So that is used for larger systems than you would want to use C for. So C++ has a lot of features to support larger programs and larger teams, with object-oriented programming specifically that we would talk more about in second semester programs. So servers running websites or things like that, performance critical applications, again, that need to be super efficient, not waste any time, not waste any memory space, things like that. C++ is great for all that kind of stuff. Large games, like with the Unreal system, if you know anything about game development, the Unreal system allows you to use C++ programming in it for large AAA games that you run on a PlayStation or something like that. Right? We use C++ for all those kinds of things, big, fast, important projects. Okay, now after those languages were developed, and this slide is more or less in historical order, there's C#, which is another advancement on that. It's kind of like they took the two plus signs and put them together, and now you've got a hashtag, if you see how they named that for that inside joke. And so C# is specifically a programming language for complicated Windows-specific applications. It was made by the Microsoft Corporation. Windows servers with the .NET system are written in C#. Smaller games like you might have on a mobile device, like a smartphone, written in the Unity system. You can write C# code in Unity for your mobile games. So there's some cases where you use C# a lot. Java. Okay, so we talk about Java once in a while. Very, very common, very, very popular. That's used on large, secure applications. Again, things you really want to make sure there's no buffer overflows. So you've got Java stepping into the picture for that. Things on the servers, maybe not so much local applications, but server-side stuff, web clients. Java is great for cross-platform development. So if you need a program to run both on Windows and the Apple operating system, Java makes that very, very easy. Mobile applications, like originally Android, all the programs were written in Java. Nowadays, you also have what's called the Go language, but originally, all the programs in Android were written in Java. So lots of uses for that. There's also Python. There's also this language called Python, which is better for very small applications and scripts for the web. It's very easy to get in and learn a little bit of Python. And so that's become very, very popular lately. But Python doesn't have the capacities for supporting larger teams and larger projects that we have in the object-oriented programming languages like C++ and Java and C#. So Python is great. Very, very popular nowadays for small applications, working in the sciences, working in artificial intelligence, working in media and producing some video files and some image files and things like that in other fields. So Python's great to get into. There are many, many schools that use Python for their first semester programming. But then when they need to deal with object-oriented programming in larger systems, then they have to switch back to something like C++ or Java in their second semester. So Python's easy to get into, but maybe a little bit limited further down the road. So as I make this recording, I'm recording this in 2022 in the fall. These 5 languages that are on screen right now are the most popular top 5. This right here is the top 5 most popular languages right now. And, you know, depending on the month, depending on the year, the specific order in the top 5 might move around. But I'll say this, it's pretty consistent nowadays. Once in a while, in the distant past, there were lots of languages being developed all the time, and like almost every year, a new hot language that's going to revolutionize programming would pop up, and people would be very interested in that for a short period of time, and then there'd be a new language that was super hot and super popular. That was maybe like 30 or 40 years ago. Nowadays, it seems like we've pretty much settled on these languages are very good, and they handle most of the problems we need. We've developed lots and lots of software with these languages. And so it more or less looks like nowadays it's pretty stable that these are the languages that are going to be most popular. I'll say this, right? The ones that are most similar to C++, C that came just before the language in this course, of course C++, the one that we've actually been studying all along, and then Java, the one that came right after it in the 70s, the 80s, and the 90s, those were the top 3 languages for fully 20 years running. From 2002 all the way up to 2022, those were the top 3 languages the whole 20-year span. And sometimes one of those would be number 1 or something else, and C++ was number 1, and then Java was number 1. But those were actually the top 3 languages for fully 20 years, very, very consistent. Now, just this year, just a couple months ago, Python became the number 1 language. And then C, C++, and Java are now number 2, 3, and 4. So Python, again, very, very popular. A lot of people like it a lot. It has now become the number 1 language. Maybe that will continue in the future. Maybe one of these other languages will become number 1 again. But the languages, again, very, very similar. And that's why I like starting with C++, because it's kind of in the middle of the most popular languages. And it makes it the easiest to step into one of these other languages, depending on what workplace you get employed in and what particular type of application you need to make. Now, as a little thing, right, the interesting little detail here is the C language, which is the oldest one, and people look at it and go, nobody writes anything in C anymore, except for operating systems like Windows or Linux or Android or Apple, just that stuff, right? But in 2020, C once again became the number 1 most widespread, most popular language for an interesting little reason. Again, it says here, you use C for embedded systems like hardware. For example, that's the language you use to write the software that runs ventilators and hospital equipment. And boy, that was important in 2020. So at least for 1 year, C was the most in-demand language. You know, and then that issue kind of went away a little bit, and now Python's the number 1. But they're all important, they're all useful, they're all used in a wide variety of applications, so you ought to be aware of them. And I am glad that C++ gives us a good starting point to very easily pick up any of these other ones. Okay, so reminding ourselves of some major philosophical principles in this first semester of Starter C++ programming. And this right here is the biggest one. We brought this up, I think, the very first week of class. Don't repeat yourself. As far as I'm concerned, the don't repeat yourself principle is the number one issue in computing. We are trying to get away, historically, from human beings doing repetitive tasks. Computers exist for them to do the repetitive tasks and not human beings. So once again, don't repeat yourself. Remember the DRY principle, DRY for short, is the principle that any logical job should be done in only one dedicated piece of code. And that makes your programs faster to write because you're not repeating yourself, shorter for somebody else to read because there's less code there, fewer opportunities for bugs to creep in, right? The less code you write, the less chances there are of mistakes, great? Easier to fix because if a job is in just one part of code, you know where to go to fix it if there's a bug. And once again, why are computers on Earth? Computers are made to do repetitive tasks instead of people, of course. So that's what you ought to use the computers for. If you find yourself typing the same thing many times, try to think of a better, shorter way. And you see, now we can specify exactly what we mean by a better, shorter way. Use a loop. Use a function. Use a modular function. If I'm doing a whole lot of compute the average, write one single function that computes averages and then just call that function. Don't keep rewriting the add stuff up and divide it job. Put it in one function and then just call the function anytime you need to do that job again. If you're doing something repetitive, put it in a loop. Call a function. That's exactly what you want. So we have a bunch of tools in our toolkit now to help us out. And again, if you're ever doing anything on a computer, I'm not even just talking programming, and you find yourself doing it repetitively, there really ought to be a better way. Take a step back and see if you can find the better way. Again, this principle, I didn't come up with it. That's from the book, The Pragmatic Programmer by Hunt and Thomas. A great book. If you get a chance, look up The Pragmatic Programmer. That's just one of the many great principles in that book, and you can see all the other stuff too. Okay, remember the different data sequencing strategies. You have data coming into your system or data being processed, and we have two primary ways, two different ways of handling and managing that. So item number one, you might have count control data. That's where you're getting the size at the start, getting the number of things you have to deal with up front. And if you know the number of things in advance, then you can use a for loop to process the data. That's what a for loop's for, obviously. And examples when we've done that, array definitions, you define the size of the array. You have a constant for the size of the array. You can use that in a bunch of for loops to process your arrays. Pascal strings. Now I know we've never talked about that before, but there's a language called Pascal, and they have a particular format for their strings where the first byte is a number for how long the string is. And then you have that many bytes for the actual contents of the ASCII characters in your string. So that's a legitimate strategy. It works perfectly fine in Pascal to have the size of the string at the start. Now that's not how our strings work in C or C++, but that's how they work in other languages. User input. Many of our examples have started out and asked the user, how many students do you have? Okay, and I've got 25 students. Now there's a for loop to enter all their grades, right? So that's legitimate. Ask the user up front, how many things do you have? We've seen that recently in labs like 7.3 and 7.4.2, and my students can go back and look at them again to review examples of count-controlled loops. But of course, the other strategy would be sentinel-controlled data, where you have a special marker at the end of the data to tell the system this is the end. You just start processing the data, but you're looking for that special sentinel value. Now, in that case, if you don't know how many things there are going to be in advance, now you've got to use a while loop to process the data. And your while loop is going to say, while I'm looking at stuff and it's not the special sentinel value, keep going and do more processing. So we normally do that for file handling. Normally you open up a file and you don't know how much stuff is in the file. So you start processing it with a file loop, and you're really looking for the special marker at the end of the file that we call the end of file marker, the EOF symbol. And again, it's invisible, you never actually see it, but that's what's controlling our while loops as it hunts for the end of the file to stop. Now that is also how C strings are set up. C strings are set up as character arrays with a bunch of ASCII characters, and at the end, the null terminator, which is actually the number 0, to mark for our programs where the string ends. Notice how that's the reverse of how Pascal strings are set up. But it works perfectly fine in C strings. Special marker at the end. And we have had a whole bunch of examples for sentinel-controlled user input, whereby we say to the user, you don't have to count up how many things you have. Just start entering scores, and when you're done, type in -1 or 999 or some kind of special number to indicate you're done. So you can totally use sentinel-controlled data for user input. And maybe that's even smarter because then it lets the computer do the repetitive job of counting up how much stuff there is. And the human doesn't have to in advance. That's nice. So we've seen that in labs like 7.1 and 7.2 and 7.4.1. And my students can go back and review that if they want to see examples of sentinel-controlled loops. So I would say that, like for example, my students, when they get to the final exam, there's going to be a programming challenge where there's going to be some kind of input, some kind of data sequencing. Either one of these is fair game. So make sure you're familiar with both count-controlled and sentinel-controlled data sequencing, and you can possibly do either one on my final exam as one example. There you go. Make sure you can handle either one on the final exam programming challenge. Definitely. Okay, we get to chapter 6, right? We get to the halfway point of this first semester, and there's a big transition to modular programming. Up until that point, we were writing programs where all of the statements were in the main function, and it was starting to get very, very long. Getting too long really to see on screen at once, too long for a human being to memorize all that stuff. And at that halfway point, we said, don't do this. Don't do this anymore. You're never going to do that. Professional programs are never going to look like that because they're much, much longer, and you've got to handle that complexity by splitting it up into smaller parts. So over here on the right, we said now we're going to start to write separate functions. Each of these functions should do one single job, one single well-defined job here. And we said, do this. Do expect always, forever, to modularize your programs in small little sections. And then you can parse out the work to multiple programmers, perhaps. But more importantly, you can mentally focus on just one little thing at a time. You're trying to fix a bug or add a feature. Everything you need to worry about is in this one function. The only data that you can access is just what's being handed in the parameters. Because by default, you don't have scope. You don't have access to other functions' data, which is good, because then you don't have to worry about it. Just look at the variables and the parameters. That's the only access you have, and therefore, the only thing you have to worry about. And so that mentally focuses us and really solves the problem of having overly complicated programs. So definitely expect to do this all the time. That is what programs look like. A big transition point for us halfway through the semester, but that's what programs really look like. Let me emphasize this again. This is so important. So I really want to highlight it again. Well-defined functions. They should do one logical job. You should be able to express very clearly and very quickly what the one logical job is. Print my name. Print the menu. Compute the average. Get the total. Get input from the user. Print the table. Things like that. So something that's one very short, very clear English phrase, probably a verb phrase because functions are something that does something. So one single, easy to describe logical job. I don't want to print the table and also compute the average in one function. That seems to be two jobs to me. So one job per function. There should be a very clear name to it, right? If it's one single job, it should have a very clear name. It shouldn't be ambiguous like do some stuff. Like that's a terrible function name. It kind of indicates that you're not entirely clear about what the one job was supposed to be. So come up with a very clear name. I usually spend more time thinking about my names than anything else in my programs. Once you've got a good, clear name, the rest of it's going to be very easy because you've got a mental idea about what the goal is. So there's power in good names, and you should use that. A good function really ought to fit on one screen. You ought to see the header with the name and the parameters. You ought to see what the return statement looks like and everything in between on screen at one time. You want to be able to visually take in the whole thing on screen. If your function is too long to fit on screen at one time, that's a terrible sign. And I've been recommending that your functions be around 7 lines long. 5 or 6 or 7 or 10 or 12 lines is okay. Around 7 lines long, because psychologically, that's people's short-term memory. It's been discovered that people can hold about 7 things in their head at once. And so if you have 7 statements in a function, people can actually understand that in their head at one time. Is that a hard and fast rule? Of course not. Of course not. But that's my personal recommendation as a programmer. Around 7 lines is easy for people to mentally digest. Try for that, I would say. Really try very hard for that in how you have well-defined functions. Great. And that's the course. So at this point for my students will be getting ready for their final exams, and I have a practice final exam on our learning management system, so I'd ask my students to take a look at that. And if they have questions about it, ask in one of our last class sessions that are live, or email me, or sign up for an office hour or something like that. And as usual, getting some more practice in is the very best thing you can do. So I've picked out a couple of programming challenges in this last chapter that we got to in this first semester, this chapter 7, where you've got arrays and you also already know about functions and all the other things. So challenge 7.1 or 7.4 or 7.9 would be really great practice for handling arrays, handling lots of data, and processing them in the ways that we normally do. And as a reminder, again, as I've said in the last 3 slides here, be sure to organize any program you write now in a modular style with separate functions for input and output and processing. Even if the assignment doesn't say that, they're not going to, because we all know we need to do that anyway. So make sure you're practicing separating the work out into separate functions, as we always do. And you're working with arrays, and you're getting some practice passing the arrays into the functions that need to do the processing. So these are really great challenges. And if you do all those and you find them very easy, go on to some other ones. I mean, maybe practice some file handling challenges that are in the book. It's all good. But those would be my top 3 recommendations. Great. We've arrived at the end of C++ programming semester 1. So look, if you've watched this far, I'm going to congratulate you. You've been doing a lot of work to get here. So we've developed a very nice package, I think, of starter tools and concepts for beginning programming. We've got input and output happening in like chapters 2 and 3. We've got decisions and loops happening to do repetitive tasks in chapters 4 and 5 or so. We can make modular programs with separate functions now that are well-defined and short and easy to understand. We can process lots of data with arrays very easily, actually. Maybe we can get the input automatically by reading files, by doing file handling. So many good stuff we have in this initial toolkit in semester 1 that you can actually do a lot of work. You can do a lot of work with just these basic tools that we refer to as procedural programming that have been in the C language for all this time. Now, don't forget, semester 2 is about object-oriented programming, where we add more features to help support larger teams and larger programs than we can do with just the procedural stuff. And you can do it, but so many more good features in semester 2. So I do hope that you'll join me again. Thanks so much for watching this first semester of programming. I do hope you'll join me again for C++ programming semester 2. And if you do, I'll look forward to seeing you then.